All right, good afternoon, everyone. Let's start. And so first of all, I just want to remind of everyone that our midterm project report due is on the Friday after the spring break. So if you haven't started doing something with your project, so please collect the results and wrap up things. I'll suggest you to wrap up things before the spring break because I don't want you to spend any time in spring break doing those project things or homework assignments, right? But even after spring break, you still have 1 week to wrap up things. Right? Just a reminder. Okay, so let us continue with the graphical model inference. In the last lecture, we have finished the introduction of the general definition of 2 types of graphical models. One is called Bayesian network. Essentially essentially directed graphical models. Right? There is an arrow between the nodes. Another type of graphical model is called undirected graphical models, where you don't need to concern about the edges, and but you need to define the potential functions on clicks or maximum clicks over the graph. Okay? So, but at the end of last lecture, we talked about the computational issues on the graphical models. So, generally speaking, the computational task on the graphical model is to compute the posterior of 1 or more subsets of the nodes given the observed nodes. So the observed nodes just means, okay, given observed data, right? So take this simple graphical model as an example. It only contains 2 nodes, X and Y. Suppose you have collected data about Y, meaning that we're gonna shade Y, meaning that Y is observed. Then the interesting question would be, how do we get the posterior distribution of the remaining node X given Y? Right? So we know that according to the Bayes rule, the posterior distribution is the joint distribution divided by the marginal distribution of the observed nodes, right? So the joint distribution, according to the decomposition structure specified by the graphical model, it is really fairly easy to calculate. So the major challenge is to compute the denominator, which is essentially the marginal distribution of the observed nodes. Right? So from this simple graphical model, you might say, okay, this is not a problem because we just marginalize this joint distribution with respect to X, that's it, right? But let us consider a little bit more complex graphical model, which is the chain graphical model. So we assume that we have a big N nodes in our graphical model, and they're connected via chain, right? Between every pair of successive nodes is an edge, right? So we know that because it's undirected graphical model, right? So we know that associated with every maximum click here will correspond to a pair of the successive nodes, right? Is a potential function. So like the potential function defined on this pair is denoted by psi12, x1, x2, right here. And the potential function defined on pair of x2, x3 is denoted by psi23, x2, x3. And you continue until you have the potential function defined on the last pair, right? Psi n minus 1, n. Right? So z here is the normalizer. So let us assume all those nodes are discrete. Each node can take k possible states or categories, right? And so that each potential, because each potential is defined on a pair of nodes, so each potential function essentially is a k by k table, right? For every pair of the configuration, you got the potential function value. So suppose we're given a particular node x of n, right? Which is in general in the middle, right? If we want to compute or infer the marginal probability of that xn takes some particular value, say it takes 3, right? And let's see how can we do this marginalization and what is the cost of the naive computation, as we explained in the last lecture, right? End of last lecture. We know that here is the joint distribution over all the big N nodes. So now if you want to compute the marginal distribution for one particular node, this small xn, you're gonna sum over the configurations of all the remaining nodes in the graphing model, right? Except x small xn, right? So we have made some kind of analysis about the cost. Remember, each node can take k possible states or categories, right? So you got for every particular choice of xn, say xn equals to 3, you're gonna sum over all possible combinations of the remaining n big N minus 1 nodes. Right? It will take k to the power of n minus 1 summations, right? But the choice of xn, the value of xn, has k choices as well, right? So the total cost will be k times k to the power of big N minus 1. So it end up with k to the power of n. Right? So you can see how horrible this cost. Right? It grows exponentially to the length of the chain, or the number of the nodes in the graphing model. And this is actually just a very simple structure. You're making very strong assumptions about conditional independencies, right? But if you just perform naive computation, even calculating the marginal distribution for any node, it takes this much cost. Of course, it's not practically useful. Right? So the natural question would be, okay, how can we lower down the cost, right? How can we make the computation a lot easier, right? A lot of practical, right? So the key idea is as follows, right? Because many terms are repeated in the calculation, right? So we do not want to repeatedly retrieve those terms and multiply with other terms and add them together. And these are just the summation of a bunch of products. So the natural idea would be, can we leverage the so-called distributive law? Everybody learns distributive law from the primary school. So that we can save the products and the sum operations as much as possible. Take this sum product as an example. I suppose you are summing over the values configurations of two variables, right? Variable x1, it might take two values, a1, a2, and the variable x2 can take two possible values, b1, b2, right? If you just naively enumerate all possible configurations of each variable, right? You do a1, b1 plus a1, b2, a2, b1, a2, b2. Right? We got 4 products and 3 summation operations, right? But from here, we see that, okay, b1 is repeatedly showing up, right? And so is b2, and so is a1, a2. So why not we just first fix the variable 1's value, right? A1, say a1, then we just merge the terms, which is gonna be multiplied to a1, so we got b1 plus b2, right? And if we fix the first variable's value to a2, you got the same summation, right? And finally, just merge them together, you find that, okay, I only need to first sum up b1 and b2, and then sum up a1 and a2, and then do the product. We can see that actually only needs 2 summations, 1 product. It's like dramatic reduction of number of operations as compared with the naive approach. Right? Does it make sense? Okay. So now let's see how can we apply this idea to the chain graphic model. It's actually all the smart inference under the graphic models are leveraging this basic idea. So I'm gonna use a concrete example. For example, why is this here? A new page. Still like that. Okay. Anyway, so suppose I only have 4 nodes. X1, X2, X3, and X4. So I want to compute the marginal distribution of X4. Okay. I mean, just following the same definition, I just want to give you a concrete number, 4, rather than big N, to showcase how this calculation trick is doing. Right? So according to our definition, let's just take out the normalizer from, and then we're going to sum over X1, 1 to K, X2 from 1 to K, X3 from 1 to K. Then you got this psi12, X1, X2, psi23, X2, X3. Oh, let me switch that. Oops. Looks like it doesn't look better. Let me use this. Okay. N times psi 3, 4, X3, X4. Okay. This is just the original definition. And we know that if you just enumerate all possible potential function values and do the summation, that would be very, very ponderous, very costly. But how do you see computation? We can do a kind of a nested sum from left to right. Okay, we do that. Like let's just fix x2 and sum over the first potential function. Oops. Okay. So we can sum over the first potential function defined on x1, x2. And we just fix x2 and then sum over psi12 at x1. And then you can see that by doing so, for different value of x2, right, you do this summation. You actually end up with a function of x2 only. I'm going to denote this function by mu alpha x2, right? So you give x2 equals to 1, you sum over this psi12, you got the value, right? We give the value x2 equals to 2, you sum over this psi12, you got the value for x2 equals to 2, right? So actually you kind of like aggregate the table, the k by k table to one column table, right? So that we can get the first intermediate results, which is only associated with x2. Right? So next, we can conduct the second level of summation over it. Right? That means we can involve psi23. Right? So let's multiply this guy with psi23, x2, x3, and then sum over x2. Right? Right? So what's the benefit of doing this? Right? What's the benefit of first do this inner level summation over x1, and then take out this intermediate function or result and multiply with the next potential function psi23 and marginalize over x2. That's the benefit. The benefit is like this. If you take x3 equals to 1, well, we just do the summation over x2, right? Do everything. Right? And now, if you switch x3's value to 2, of course, side to 3, the potential function value will change. But the inner summation is this value, this mu alpha x2 has already been computed, right? You don't need to recalculate this inner summation anymore. You just need to read out the intermediate results from this mu alpha x2, right? And same thing applies that when x3 equals to 3, right? You only need to change the value inside the 3. You have to change because you change the value of x3. But when you sum over x2, again, this inner summation has already been done. You just need to read out the catched result, right? So this way, we don't need to repeatedly compute the inner summation. Does it make sense? It's just the application of the distributive law, right? In this way, like, if you do this naively, you can imagine you have to repeatedly compute this inner summation, right? For different x3 values, like if we say x3 equals to 1, well, you multiply this guy and then multiply with this inner summation, right? And do an inner summation. When you have x3 equals to 2, well, you change this value, but at the same time, you have to recalculate this whole inner summation again. So there's a lot of like duplicated computation. However, if you do this nested summation beforehand, right, because you have already catched the results, every time you switch to a different value of x3, you're going to just read out the corresponding value of mu of alpha, multiply it, and do the summation. Does it make sense? Okay. So again, if you do this second level summation, you actually have marginalized out x2, right? So you get a function of x3 only. Okay. So for we got a function of x3 only, right? But this function, you can imagine like different value of x3 here actually includes the aggregation of all the configurations of previous nodes x1 and x2 in their potential functions. And what's the next step? We have finished the 2-level summations, right? Remember, we want to compute the marginal distribution of x4. You just add one more level of summation, right? Just the sum. Over this mu alpha x3 times the last potential function x3, x4, right? And this sum over x3. Then you get the marginal probability of x4, right? And again, I want to emphasize, right? You take x4 equals to 1, of course, the corresponding psi 3, 4, the potential function will change. And you need to enumerate all possible of x3 and read out the values of the mu alpha x3 and sum over it, right? However, when you calculate the marginal probability of x4 equals to 2, so of course, now x4 equals to 2, this whole psi 3 function value is changed. But for this part, you don't need to recalculate anything, right? You just read out the catched result here, right? You change what? You change x1. X1 is marginalized out at very first step. So here we want to compute the marginal distribution of x4. So you're gonna sum over x1, x2, x3. Right? X1 is supposed to take like k values. During your marginalization, you have already go through all possible values of x1. Right? The benefit here is that, okay, as long as you can smartly catch those intermediate results through this nested summation order, you won't need to recalculate from scratch. All you need to do is that, okay, you just change the configuration of x4, you have to change what you have to change. Right? For the remaining part, they have already been catched, just read out. You don't need to recalculate. And what is what? Oh, alpha is just a random symbol. Yeah, I just random draw a subscript to denote, because later we'll define this summation result. You see that we kind of like summarize or aggregate this potential function product from left to right, right? So we denote it by alpha because we view it as kind of message sent from x1 to x2, x2 sent to x3. So we denote by mu alpha. And right now I'm gonna introduce another way to sum over from right to left, and we denote it by beta. That's it. Nothing other means. Yeah. And we'll later discuss the complexity. But anyway, this is just an application of the distributive law we just mentioned. Does it make sense? If you, Yeah, yes, exactly. Well, implement, it's better for you to use matrix multiplication to do that. I mean, if you're uncomfortable, you can try to derive these things by yourself, like what I did. I'm pretty much sure you will not feel like this is a question. Any question? I thought you. Yes, because the potential is defined over x1, x2, and x2, x3. That's why you can do that. If your potential defined over x1, x2, x3 jointly, well, you cannot do that. It's actually, you're essentially leverage the structure of the part. No, it doesn't always. And later we'll kind of like talk about the general structure. If the general structure is a tree, it's very efficient. But if it is not, and it cannot guarantee like exact results. It can only be some approximation. The tree, what? Yeah. I mean, right now we just look at this is actually essentially is also a tree, right? The chain is a tree. But imagine that you just have a tree. The root node may have like 10 children nodes or like 11 children nodes. But as long as it is a tree, all those tricks apply. Okay, so now as we just mentioned, right? So we can see that our nested summation from left to right and catch the intermediate results can efficiently reduce the cost, right? And we can denote those intermediate results. So you can see that you essentially calculate those results from left to right. Right? Every time you marginalize, you're starting from marginalized psi1, 2 across x2, right? So it sounds like, okay, you're aggregating the product of the potential functions up to x2. So we will, I mean, just for better visualization, we will is a message sent from x1 to x2. And then given your summary up to x2, which is mu of x2, you multiply with the potential function defined by x2 and next node x3. So you marginalize over x2, you got a next intermediate results, which actually summarize or aggregate the results up to x3, right? So we denote or we define this intermediate results as a message sent from x2 to x3. You can continue to do so, right? You finally got your message sent from x3 to x4. Right? So this message is computed from the left to the right. So we usually call it forward message. So now let us look at another case. Right? We talk about the same graphic model. It's still x1, x2, x3, and x4, right? And now this time, I want to compute the marginal distribution of x1. According to the definition, it will be sum over x2, x3, and x4. Psi 1, 2, x1, x2, psi 2, 3, x2, x3, and times psi 3, 4, x3, x4, right? So of course, if you just apply this naive formulation, you're going to be very costly to compute the marginal distribution of x1. And can we apply the similar kind of trick to efficiently compute P of x1? The answer is yes, right? But right now we need to make this order from right to left. Right? So first of all, we can look at the last potential function, which is defined on x3, x4, right? x3 and x4. So we're going to marginalize out x4, the rightmost node. Fix x3. That means you can start from here. And of course, different x3, you're going to have a different results. So after you do this marginalization over psi 3, 4, you actually get a function of x3 only. Right? So here I use beta just to denote, okay, now the calculation direction is from right to left. So, and this mu beta of x3 function, right, actually aggregate all the potential product from the last node up to x3. Okay? And next, we're gonna multiply this intermediate results with one potential function to the left, right, which is psi 2, 3, x2, x3, and we conduct the second level summation, which is over x3. Right? It's the same thing. And then after that, we actually got a function of x2 only, right? So denoted by mu beta x2. So again, the benefit is here, like if you change the value of x2, like x2 equal to 1, you just need to vary the value of x3 from 1 to k and multiply the corresponding mu beta function, right? But now if you change the x2 equals to 2, you just need to vary this potential function. But this inner summation has already been computed and cached. You don't need to recalculate again. That's the benefit. So if you just calculate this mu beta of x2 function for all x2 values, right? You finally got this mu beta x2. Again, it actually summarizes or aggregate the product of the potential functions from the rightmost all the way up to x2, right? So we define this as a message sent from x3 to x2. And then to calculate the marginal distribution for x1, we're going to do the final level of summation. Right? So we're going to multiply with the potential function here. So 1, 2, x1, x2, and then just marginalize over 1 over x2. Right? And then you get your marginal distribution of x1. Right? So you can see that we can also pass the message from right to left. Right? And this nested structure actually is the same. So now I want to ask, right? Suppose I want to calculate marginal distribution for a node in the middle. Suppose I got graphing model, I got a bunch of nodes. So this is xn. How can we efficiently calculate the marginal distribution of xn? Yeah, both directions, right? So when for x4, right, it is on the rightmost, well, you just calculate the message, calculate the pass message from left to right, right? And from the leftmost nodes, x1, right, you just calculate and pass message from right to left, right? But if your node is in between, right, is in the middle, well, you can use the same method, right? Just calculate pass the message both from left to xn and from right to xn, just multiply them together. That's it. Any questions so far? This is just the practice of distributed law. You actually don't need to do that. You just need to calculate all the messages. Once all the messages are ready, and for every particular node, you can just multiply the forward and backward message. That's it. So those messages are reusable by every node. You don't need to recalculate. That's a good thing, and it's a benefit of this. Mm-hmm. Oh, are talking about the order of the computation of the message? Yeah, I mean, the order will be, okay, I'm gonna starting from left and calculate message all the way to the right. And then I'm starting from right, calculate message all the way to the left. And in this pass, I calculate message from every node to its neighboring node. And once it's done, okay, I can pick up any node, multiplying the incoming message to that node, and then you get marginal distribution. And for the more general structure, like tree structure, you have to define right order. So basically, you have to specify the tree structure. Like you can pick up any node as your root node, and you know who is leaves, who is child, or who is leaves, who is the intermediate node. And at the beginning, we're gonna start from the leaf nodes, and all the way up to the root node. And then when you arrive at the root node, you just distribute a message all the way down to all the leaves, and then you finish the calculation of all messages, and then you can just merge messages to compute any marginals. Does it make sense? We'll get to the algorithm details in the general tree structure later. Yes. Yeah, like for example, this is xn minus 1, and this is xn plus 1, right? So we know that okay, there are going to be two messages. One is forward message, one is backward message. You remember the forward and backward message is just the, okay, the forward message just means I'm gonna I'm gonna summarize the product of the potential functions all the way up to xn. That's it. And the backward message is just the sum of product of the potentials from the rightmost nodes all the way down to xn. Okay? And then you just multiply them together. You got all the results because you got the summation over all the remaining variables. Is not potential function. It's just the mu of alpha xn times mu of beta xn plus 1. Oh, sorry, mu beta of xn. That's it. Because when you calculate this message, you essentially have already multiplied with this potential function. Let me take a look at the general formulation. It will have a better structure. Does it make sense? Okay. So in general, like if you want to compute the marginal distribution of the node in between, right, xn, and we know that you're going to marginalize over all the variables on the left of xn and all the variables on the right of xn, right? Right. So, and remember, all the variables on the left of xn do not overlap all the variables on the right to the xn, right? So that means your marginalization or summation over those two groups, one group is on the left, one group on the right, are independent. They're not depending on each other. So that means, okay, you can decompose this summation in two parts. One is the summation over all the variables on the left, right? The other is summation on the potential product of all the variables on the right. But remember, xn is fixed, right? Given any value, xn is fixed. Does it make sense? Right? And then you can first, and we denote all the summation of the potential product on the left by the message sent from the xn minus 1 to xn, which is denoted by the forward message. And all the summation of all the variables on the potential product on the right as the message sent from xn plus 1 to xn, which is called backward message. That's why we can multiply them together. And we have used that concrete example to show that this summation essentially has this nested structure. Right? We just need to first aggregate the first potential function, right? And then you get intermediate results. You multiply the second potential function, and with this intermediate results, and you do it step by step until you reach xn. Right? And similarly, if you do this backward message, you can start from the rightmost potential function, you aggregate the rightmost variable, you get intermediate results, you multiply the second rightmost potential function, and you get intermediate results, and you do this from right to left until you reach xn. Okay. So that's where this nested structure show, right? So we can see that we can first, given x2, fix x2, which is the sum over psi1 x1 in its first potential function, psi1 2, right? And then you get this intermediate results, then you multiply it with the second potential function psi2 3 over x2, you get the second intermediate results. You do this again until you reach xn, right? This is exactly what we have done in the for variable or for node case. And similarly, the backward message, you can start from the rightmost potential function, okay? n-1, and you fix xn-1, you just sum over xn, right? You got intermediate results, and then you multiply the second rightmost partition function, potential function, which is psi n-2 n-1, right? And sum over n-1, you get the second intermediate results. You do this from right to left until you reach xn. That's the idea. And then finally, you get the message from left sent to xn, and from right to xn. You just multiply them together. Does it make sense? I mean, if you still feel a little bit uncomfortable, don't worry. Just do something like that by your hand. You get it. It's just the application of distributive law, nothing else. In this way, as we just mentioned, right, for better visual looking or better visual understanding or intuition, right, we kind of like denote this summation of the potential functions product all the way up to the current node xn by this message mu alpha xn. And again, the summation or an aggregation of the potential product from right to left is denoted by the backward message mu beta xn. So the good thing is that if we look at this nested computational procedure, we can summarize some recursive formula. That is, the message sent from xn-1 to xn essentially is just multiply the potential function defined between xn-1 and xn with the message sent from xn-2 to xn-1, which is message mu of alpha xn-1. Okay. Why? Because this guy actually represent the aggregation of the potential product up to from x1 up to x-2. Right? So this is just a recursive definition. And if you want to compute xn-2, well, you just need to update. You just need to multiply the message sent to its previous node xn-3 with their potential function, and then sum over xn-3. So you can see this recursive structure. Right? And similarly, if you calculate the backward message, the same thing. Right? We know that if we want to compute the message sent from xn+1 to xn, this backward message, right? So it is equivalent to multiply the potential function defined on xn and xn+1 with the summation from the rightmost node all the way up to xn+1. Right? And this result, aggregation results of the potential product from x big N to all the way up to xn-1 essentially is the backward message from xn+2 to xn+1, which is denoted by mu of beta xn+1. Okay. So there's another recursive formula. Here, let's assume there's no cycle. Right? And later we'll talk about if there's cycle, if there's cycle, then this computation is not accurate. The other way, it's not correct. Because of the not cycle, so that means you can decompose this summation in this nested way. Otherwise, you cannot decompose. Does it make sense? Okay, great. So now, in this way, we have figured out a way to efficiently compute this message, right? We can start from the leftmost node and sequentially calculate the forward message from each node to its next node, okay? One by one, until you arrive the rightmost node x beacon. And similarly, we can compute the backward message from the rightmost node x beacon to every previous node, okay, until you arrive at the first node. Then you'll have all the forward and backward messages, right? And for any intermediate node, xn, you just multiply the forward message and backward message sent to xn. That's it. And sometimes if you do not have the result for the normalization constant z, well, what you need to do is just marginalize over xn by this message product, and you get normalization constant. So now I want to ask, what is the cost? If you take a look at the cost, right? So every time, because this message is ready, right? And what we need to do is just multiply this message with the potential function defined on the current node and the next node, right? And then you sum over xn minus 1. And it will take for one particular xn, it will take k operations, right? And if you enumerate all possible value of xn, it takes k squared, right? Then you finish the computation of the next message. You just go over the chain for twice, right? So the chain length is n. That's why the final cost is nk squared. Okay. Let's compare with the exponential cost. As we mentioned, naive computations, k to the power n. Now it is linear in n, right? This is much more efficient. So here, we want to give a summary. So if you want to inference on the chain graphing model, if you want to efficiently compute all the local marginals, we can compute and store all the forward messages from left to right. Then we'll compute and store all the backward messages from right to left. And then we can compute, if you don't know the normalization constant, you can just marginalize at any node xm, then you get your, then you just, for any node xn, you just retrieve the forward and backward messages, you calculate marginal distribution. It's very efficient. So maybe you have heard this algorithm before. In some discipline, like commonly used hidden Markov models. This is called a backward and forward algorithm. And you can use similar procedure to find the maximum, the configuration of those variable values, which can maximize the joint probability. This is called a Raterby algorithm. If you're from EE's department, you should at least heard of this term, Raterby algorithm. Anyways, it doesn't matter. Okay. Now I have a question: how to infer? Suppose you have done this, right? How do you infer the margin of two neighboring variables? Suppose dot xn and xn plus 1, right? What if I want to compute the marginal distribution of two neighboring variables, xn and xn plus 1? Any thought? That's exactly right. So it's relatively easy. You just will this guy as a whole, right? You just look at the messages incoming to this node. Well, of course, you need to consider the potential function defined on that. So it is essentially, well, we have to put proportional to the forward message coming to xn and backward message coming to xn plus 1, and multiply their potential function, which is psi n plus 1, xn plus 1. Okay. Okay. Any questions so far before we go to a more general inference algorithm? Is everyone comfortable? If you do not, if you still feel a little bit uncomfortable, I mean, just to follow the concrete example we have shown, like just to use your pen to derive it yourself. You get it. It's not I mean, it's not mysterious at all. It's just the mechanical application of this recursive nested application of the distributed laws. Yes. Yeah, we're going to talk about that. But the key is that if you can efficiently calculate the marginal distribution for any nodes, and even you have fixed several nodes which are observed, this computation is still very, very easy. We're going to reach to that point later. Okay, so now let us generalize this idea to trees. Okay. Again, I want to emphasize that this trick is very useful and very efficient when you deal with a tree structure graphing model. But if it is not tree, it has some cycles, then it won't. I mean, you can still apply kind of similar calculation procedure, and then it won't guarantee it is accurate. It is kind of approximate inference, approximate calculation, which is usually referred to as a loopy belief propagation. Okay, so here we just gave two examples: a tree structure MRF or tree structure Bayesian network. So why do we emphasize trees? Because tree structures can guarantee exact inference. We'll see it later. Right? But here I just want to stress on the definition of trees. Trees just means there is no cycles, and the nodes, every pair of nodes in this graph is connected. I mean, there is not required that they must be there must be an explicit edge, but they must be connected. Like this node and this node, they're connected through this path, right? And there are no cycles in this graph, and this is called a tree. Why the tree structure is so important? The reason is that we can use tree structure to decompose the computation recursively. Like, for example, if you use this node as your root node, right? You know that if you want to compute the marginal distribution of this node, right? And then the marginalization over this bunch of nodes and the marginalization of this bunch of nodes are independent because their nodes are not overlapping. If they're overlapping, that means there's a path, there's a cycle in this graph. Because they're not overlapping, that means you can decompose the computation in this way and then in this way. And then you can recursively do this, right? If you look at this root, this subtree, right? Given this root of this subtree, you know, all of its children are root nodes of different non-overlapping subtrees. So you can further decompose the computation or decompose the marginalization. This is like general sense. So now here we want to we want our representation to be more informative and to be more convenient. So we introduce the so-called factor graphs. So what is factor graphs? It's just a particular type of graphs which is by bipartite. Bipartite graphs meaning that this graph contains two types of nodes, And there are only edges between different types of nodes, right? And between the same type of nodes won't be any edges. So what is the definition of factor graph? All the circles here are the random variables, like x1, x2, x3. Right? But the square nodes are the functions in a joint probability. This function can be the conditional probability as in the Bayesian network or the potential function in the undirected graphing model. Right? Like, suppose you define, suppose you are given this factor graph, that just means your joint probability of these three random variables is fa of x1, x2. So you can see that one factor node, it represents a function of the nodes that factor connects to. Like fa connects to x1, x2, that means, okay, there's a function, fa is a function of x1, x2. Then multiply fb, which is another function of x1, x2 as well, and multiply the factor of fc, a third function, which is function of x2, x3, and finally fd, a function of x3 only. So to be succinct, you can also write down your joint probability as the product of the factors in the factor graph. And here I want to emphasize again, right? One joint probability or one graphing model might have a multiple definition of factor graphs. It depends how you define the factors, namely how you define those functions over the random variables. For example, for this Bayesian network, right, from Bayesian network itself, we know that the joint probability is the marginal probability of x1, marginal probability of x2, because they both don't have parents, right? And then conditional probability of x3 given x1, x2. Okay? So if you define the product of the three probabilities together as one function, one factor function of x1, x2, x3, then this is your factor graph representation, right? Because you only have one factor which connects all three nodes. However, if you want to give a more refined definition of factors, meaning that I'm gonna represent, we're gonna define fax1 as the marginal probability of x1, fax2 as the marginal probability of x2, and fc function is a conditional probability of x3 given x1 and x2, then this is your factor graph. So the choice of factor graph is flexible. It depends how you want to map your factor functions to different terms in your joint probability. It's up to you. And similarly, I mean, for undirected graph, depending how you're gonna define the mapping or the associations between the potential functions and your factors, you might have different structures of the factor graphs, which correspond to the same undirected graphing model. Okay, any questions so far about definition of factor graph? Here? I have that because I define the probability of x1 as the first factor fa. The probability of x2 as second factor fb, right? So my joint probability is always, according to the factor graph, is always the product of all the factors in the graph. So if you multiply together, you still recover the original probability. But my point is that you can define all this product together as one function. You only have one graph. Well, of course, you can associate the three terms with three factors, then you have three factors. But when you multiply them together, they correspond to the same distribution. And now the question regarding the definition of factor graphs, because our sum product algorithm will be described based on factor graphs. Okay. So now we're gonna introduce the so-called sum product algorithm. The objective of this algorithm is to provide an efficient and exact way to find marginals of any node in this graph. And if you want to compute multiple marginals, right? Node 1, node 4, node 5, those marginals, we allow the computation to be shared, meaning that you don't need to rerun this sum product algorithm multiple times. You just run once, and then you can very easy to get arbitrary marginals you want. And the key idea here is still based on the distributive law, as we just mentioned, right? So it's just a smart usage of the distributive law. You can view as a more general framework of the chain graphing model inference, as we just discussed. So suppose you are given a tree structured graphing model, right? And your joint probability, I would say, suppose you want log a particular node in your factor graph, particular variable node x, right? And you want to compute the marginal distribution of this node x. And from the definition, that means you're going to marginalize out all the other variables other than small x in your joint probability. Okay? And because the tree structure graphing model, remember the tree structure means that there's no cycles. So if you use x, for a tree, you can pick up any node as a root node from what we have learned from discrete mathematics, right? So that means you can will x as a root node, and then all the associated factors with x can be viewed as different subtrees, right? Root nodes of different subtrees. And those different subtrees are, different subtrees may contain different set of nodes and factors. And those different subtrees do not overlap. That's the tree structure property. If they overlap, that means there is a path connecting these two subtrees. There's a cycle. So there won't be any overlapping across different subtrees. That means if you look at the joint probability, it can be decomposed according to the neighborhood of x or children nodes of x. So let us denote the product of the factors inside one particular subtree rooted by one neighboring factor node fs by this big fs. So it consists of the node x, our target node, and all the remaining variables inside this subtree. Okay? And the key observation is that, okay, x here, all the variables here are non-overlapping with all the nodes in here. Right? That's why we can just decompose as product across the subtrees. Does it make sense? The even better thing is that because we know the nodes, the variables in different subtrees, right? Remember, different subtree is rooted by the neighboring factors connected to x, are non-overlapping. So when we do the marginalization, this marginalization, of course, on different subtrees can be done in parallel, right? Because they're not depending on each other. That means we can move the summation inside the product. And here, NE is just neighboring. Does it make sense? You got let me, if you feel like a little bit uncomfortable, let me emphasize this again. The K property is that this is a tree, right? This is a tree. You can pick up any node of interest. Here is X as a root node. Then all the neighboring factors connected to X corresponds to a subtree, right? And those subtree with the neighboring factors as their subtree's root, right? And because there are different subtrees, the nodes, the variable nodes inside each subtrees are not overlapping at all. And remember, we do marginalization. We actually sum over all the variables in different subtrees, right? But because the nodes in different subtrees are non-overlapping, so are the factors. So that means their summation are just independent of each other. Right? That's why we can move the summation from outside to inside. Right? That's the key observation. So we define the summation or the marginalization over all the variables on the products of the factors inside this subtree as a message sent from the subtree root, which is f of s to x. So this is our definition. So we define the marginalization results for this particular subtree as the message from the root, which is one neighboring factor f of s. We denote it as a message sent from f of s to x. Right? And we know that because those messages they can be computed simultaneously, independently, then we can decompose the computation. Right? Our idea will be, okay, how can we find a recursive way or efficient way to compute each message sent from different neighboring factors to x? Does it make sense? Yes, yes. Chain is a special tree. For chain, like if you pick up this node, right? Well, you can see that I have two subtrees, right? We know that, okay, the summation over the product in each subtree is independent because the nodes here are totally non-overlapping. And also their factors, which here is potential functions are non-overlapping. So just you can do this simultaneously. What you need to do is that, okay, once you get those summation, which is messages, you just multiply them together to get the marginal for this particular node. So it's the same thing. It's a generalization. Like imagine for a general tree, like you might have like 3 children, 4 children, right? So it corresponds to multiple subtrees. But because the factors and the variables inside different subtrees are not overlapping at all, so you do the marginalization, you do the summation over the nodes on each subtree are independent of each other. That's why you can do them in parallel. And so you don't need to first enumerate all the values and multiply them together. You can first do the summation for each subtree and then multiply them together. This is exactly a distributive law. So this is our definition. Similar to the chain case, we define the aggregation or the marginalization or the summation of the products of the factors inside one subtree over the nodes inside the subtree as the message from the factor node to the variable node. So now we have known that for computing, we know that this marginal distribution of any variable node is simply to multiply all the incoming message from its neighboring factors. Right? So now, our question is, how do we efficiently compute the message from each factor node to the variable node? If we can find an efficient way to do that, we can kind of solve this problem. So let us look at a particular factor, f of s, which is neighboring factor to x. Right? We want to compute the message sent from f of s to x. And we know that f of s is a factor, is essentially a function. Right? It's function defined on multiple variables, including x. And suppose the other variables of these factors is x1 to x big M. Right? For any node, we can denote by x small m. So we know the factor product inside this subtree can be further written as first you multiply fs itself, right? And then remember this is a tree, right? So all the children of f of s, which means x1, x2 to x big M, can be viewed as roots of different subtree again. Right? And all the factors and nodes inside different subtrees again are non-overlapping. So that means we can further decompose their product across these children, right? So each subtree rooted by one children, we denote their corresponding product by G1, G2 until G big M. And this is still based on our pre-assumption that the whole graph is a tree. So when we look at this subtree, right, rooted by f of s, every child of s essentially is the root for another subtree, right? And different subtrees rooted by different children of fs are non-overlapping again. So we can denote the product inside each subtree by G1 to Gm. And of course, this product is determined by the corresponding root node x1 and all the associated variables inside that subtree. So we denote a big X S1, and for Gm, we denote by X, small x big M, and big X Sm. This is kind of clutter notation, but just to give you a sense, they are associated with a different set of nodes and factors again. And different nodes won't overlap. So now, if we want to compute the message from f of s to x, we're going to sum over the whole product of the factors inside this big subtree, right? And but we know that this product of these factors inside this big product can be further decomposed as factors f of s itself, and also the product inside each subtree rooted by the children of f of s, right? So again, because these guys, xs1 to xsm, they are not overlapping. So you sum, you marginalize them out, right? You can do them simultaneously. That means we can further put the summation over each subtree in parallel. That's why we can move the summation inside the product across these children of f of s. So outside, of course, you need to sum over the children of f of s, x1 to x big M, right? And then in each subtree rooted by x1 to xm, just first do the summation and then do the product. Again, because XSM, this big XSM do not overlap. That means you don't need to first do product and do summation. You can just move summation inside the product across the trees, across the subtrees. That's the idea. So, and this guy essentially is the message sent by the neighboring factors to each children x1 to xm. Right? Remember, this is a factor. This is a bipartite graph, right? So that means immediately along with xm is a factor. So this is essentially a message sent from its children factor to xm. In this way, we got a recursive rule to compute a message from a factor to variable. Does it make sense? I mean, the idea is non-overlapping across different subtrees. That's why you can move the summation inside each subtree, and then you do the product across different subtrees. That's the key idea. And we define the summation over each subtree, which rooted by a variable node, as the message sent from the variable node to factor node. That's how we define G of the summation of this guy, right? But it actually conceptually the same as we talk about message sent from factor node to root node. They both represent, okay, all the summation of the factor product inside that subtree. Does it generally give you a sense? If you feel uncomfortable for that, yeah, just spend some time looking at this decomposition structure. But the idea I have emphasized many times, just because you're dealing with a tree, right? Any subtrees across the subtrees, there's no overlapping between the factors and nodes, so that when you do the summation, you can just first do the summation inside each tree and then multiply them together. Okay. So from this analysis, we got the rule that if we want to compute a message from any factor f of s to the variable x, we just need to first prepare the message sent from any neighboring variable of f of s other than x. Right? You just calculate the message sent from neighboring variable xm to f of s, then multiply them together, then multiply with the factor f of s itself, then do the marginalization. Of course, all the neighboring nodes other than x. So if you have some time after class, please compare this to the chain graphic model. You see that this is just a special instance, the chain graphic model. So now, now the question becomes, right, how can we compute the message sent from variable node to a factor node? We know if you want to compute the message from factor node to variable node, we just follow the rule that multiply the factor itself with all the incoming message from variable node to the factor node and do the marginalization. But now the question becomes, how do we calculate the required message from variable node to factor node? So it's very similar to how we compute the marginal distribution of x. We just multiply all the incoming message to that variable node, except the target factor. So if we take a look, right? So if you look at this particular variable xm, we want to calculate its message sent from xm to f of s, right? So remember, the intermediate children of xm again becomes factors. It cannot be variables because they are bipartite graph. Right? So and our message sent from xm to f of s essentially is to marginalize the factor product inside this subtree, right? And again, this is a tree. That means each children of xm is a root node of a different subtree, right? And those subtree, again, are non-overlapping. That means if you do the summation, you can first do the summation inside each subtree, right? And then multiply them together. So if you do this, just move the summation inside the product across different subtrees. And the summation inside each subtree essentially is the aggregation of the product from in this subtree rooted by this factor node, which is by definition is the message sent from this factor node to a variable node. So that's why our final message from this variable node, factor node, is simply the message multiplication of messages from all of its intermediate children, factor children, sent to xm. Now we have figure out the rules to compute two types of messages. Right? How we compute the message sent from factor node to a variable node, and how we compute the message sent from variable node to a factor node, and they are kind of recursively leveraging each other. That's the key part of the sum product algorithm. I apologize that we kind of run over the time. But the key idea, I believe we have emphasized the key idea. It is because you have this tree structure, you can recursively decompose the product into different subtrees. And because those subtrees are non-overlapping, you can calculate their summation independently and then multiply them together. So I will highly encourage you guys to review the slides and try to recall what we can emphasize in the class, and then you get to know why the rule is discovered in this form. Okay, see you on next Tuesday.